Is the screen shared? Sir, are you able to see the screen?
Yes, sir.
Sir, no.
It's visible, sir.
Okay. Yes, now.
Right.
Yes, sir. Now it is possible.
Can we start? Sir, can I start?
Welcome back to the second day of our faculty development program. I hope all of you had a refreshing evening after yesterday's insightful sessions. It is wonderful to see you here, ready and energized for another day of learning, collaboration, and growth. Yesterday, we had a fantastic start, gaining valuable knowledge on generative AI concepts and evaluations, generative AI in creative industries, art, music, and literature. Today, we will build on that momentum as we dive into architectures in GenAI. We are excited to have another set of expert speakers and engaging sessions lined up for you. I encourage you to participate actively, ask questions, and make the most of these discussions. It is our privilege to welcome Dr. V. Masilamani, Professor in Computer Science and Engineering and Dean of Student Affairs at the Indian Institute of Information Technology, Design and Manufacturing, Kanjipuram, as today's distinguished speaker. Dr. Masilamani brings over 2 decades of teaching experience and 15 years of research expertise in fields such as digital image processing, computer vision, machine learning, and computer graphics. A proud alumnus of IIT Kharagpur and IIT Madras, he has published approximately 75 peer-reviewed research papers in esteemed journals and conferences. His notable contributions include the development of a software tool for detecting and removing forged and obscene image or video content, demonstrating the impactful application of his research. He is in charge of the Computer Vision and Machine Learning Research Lab at IITDM Kanjipuram. Dr. Masilamani continues to shape the future of AI and technology. Today, he will share his insights on architecture in Gen AI, GANs, VAEs, and transformers, a topic that promises to unravel the intricacies of these transformative AI models. Let us extend a warm welcome to Dr. Masilamani. Sir, please.
Thank you, ma'am. Thank you for your nice introduction. Good morning to all the participants. Good morning. Madam, you can allow people to speak, otherwise it will be boring.
Good morning, sir. Good morning. It's allowed,
Right.
sir. All the people can unmute and they can express.
Right. Is my voice clear?
Yes, sir.
Okay, fine.
Clear, sir.
Okay, good morning once again to all of you. So welcome to my talk on GenAI. I just now learned that you already studied GenAI through one more session. I hope there's no much intersection between this talk on GenAI and the other talk that you already had in this workshop. So let us quickly see the introduction first. What is GenAI? Maybe that part will be overlapping with what you already studied. And then we'll quickly go through the evolution of GenAI over the years. People are, talking about this GenAI very recently, and there is big hype also. But we will come to see, it is not just looked at now, but it was looked at many years back. And we will see some of the architectures of GenAI, including autoencoder, some variants of autoencoders, GAN, transformers, and some other models that are using transformers to make more generic models like GPT, DALI, DALI 2, all that. And if I'm not able to cover all the models, no issue. I'll give you the PPT. You can go through the remaining models later. Therefore, let us not rush. Let us try to understand each and every concept that we want to discuss. So what is GenAI? Generative AI, what does it mean? Generative AI is basically a program or model that generates text or image or speech signal or even computer program or some algorithms or some web code, or it can also generate some database management system, right? Like that, it can generate anything. People now saying that without employing programmers, we can make the GenAI to write the programs. But it is partially true. The statement is partially true, not fully true. Some monotone jobs can be executed by GenAI programs, right? For instance, if you want to develop a website for your institute, for yourself, then what this GenAI will do, it will pick some template that's already available in the internet, and it will take some information from you, like what is your name, what is the title of the page that you want to keep, and what are the other information that you want to keep, and all those information will be put into right tag in a proper way by GenAI, and it will give you the complete HTML code or any other language code for running the website of your company or yourself. Right? So like that. And similarly, if you want the GenAI to generate images, it can generate music, it can generate some other speech signals and so on. Well, then why you want to generate all this? What is the need? The obvious requirement is that, when you try to train a huge model like, transformer or any large language models, in particular any deep learning models, you need to feed a lot of data to the model. Otherwise, the model will not be trained properly, right? But if you want to get more data, either you employ more people and capture the data, or you make some computer program to generate data, right? So the GenAI is coming in the second category. If you want to have more data through computer program, you can use GenAI to generate such images or text or in particular any kind of data. So that is the very obvious requirement of GenAI, but there are more stronger requirements. For instance, personalized computing can be done using GenAI. For example, what do you mean personalized computing? In every domain, it means different things. For example, in teaching, when you teach a set of students, some may be quickly following it up what you're saying, some may be very slow in understanding. As a teacher, when you deliver a talk to all the students, you cannot give two different talks simultaneously to address two different groups. Whereas GenAI can do what it can do, it can understand first the requirement of the students, and it will give a different content in a different ways to different sets of people in the class. Of course, what one hears cannot be heard to the other one, so they can use microphone, speaker, and all that, right? Headset they can use. So that is possible by GenAI. It will generate, what is generation there? It will generate the content such a way that it is useful to a particular set of students. A teacher cannot do that for multiple sets of people, right? Whereas GenAI can do for multiple sets of people, multiple tasks it can generate and give it to the corresponding groups of students. Another thing that is even more important than this is only a particular use case, but there is another important theoretical motivation for GenAI, which is that we want to make our AI models to be more generic, right? That is called as artificial generalized intelligence. What does that mean? If you look at support vector machine, for instance, it can classify things into any given set of categories. For example, if you want to categorize the given image into dog or cat, it can do that. Same SVM cannot be used for classifying things into some other items. The trained SVM which was trained for classifying cat and let's say dog, cannot be used for categorizing let's say banana and apple, right? So you need to train separately again, right? So but if you look at the human brain, we are not replacing the human brain by another human brain to solve different problems. The same brain is used to differentiate dog from cat. The same brain is used to differentiate apple from banana, right? So like that, if you can make a computer program which will not be changed to solve different problems, then that will be interesting, you know. That is the one of the objectives of this GenAI. GenAI is going very close to reaching that objective of making artificial generalized intelligence, meaning single program solving many problems. And another thing, artificial super intelligence. For getting that artificial super intelligence also, GenAI is useful, but we are not reaching, you know, exactly the same goal, but we are trying to reach the goal of artificial super intelligence. What is that artificial super intelligence? You know, human brain can solve some problems with some efficiency, right? Over the years, maybe some 20 years back, we told that the computer program cannot go beyond what human can do, right? The intelligence of the computer programs will be less than or equal to human intelligence, because after all, in training, these models are trained to match the labels which are given by human being, right? So it cannot go beyond that. That is what, you know, we were thinking, you know, till last 20 years before the advent of deep learning architectures. Now, for some task, the AI algorithms are giving better solutions than the average human being. That is interesting, right? And but we want to make such artificial intelligence, you know, overriding the human intelligence or overtaking human intelligence in all tasks. That is the objective of artificial super intelligence, superhuman, you can say, super intelligence, right? Understood the need for GenAI? There are many, and important theoretical reasons are the last two. One is making the computer program as AGI, artificial generalized intelligence. The next one, even higher goal, is making it artificial super intelligence. The same brain is used to solve many problems in many domains. Can you make a single model that solves different problems? So you can stop me and interact with me at any point in time. And if I don't get any queries from anybody after some point in time, I will stop and ask queries. See, one of the examples of this, generative AI is to translate the text given in one language to text given in another language, right? The chatbot called Jugal Bandi chatbot is called as Universal Translator. It is powered by ChatGPT. And what it does is that given a query in a local language, let's say in Tamil, it is translated to the corresponding sentence in English, right? It is not just doing that, not stopping with that. Again, suppose you want to search for some meaning or the relevant paragraph in local language, and you'll have to give a query in local language that will be translated to English, and that English query will be used to search in the English documents, and then the corresponding answer in Tamil will be given as an output, right? So it's an interesting chatbot. And another motivation why we want to study GenAI, of course, theoretical motivation we have seen, but economical motivation, right? In terms of job perspective, somebody should study AI or not, or GenAI or not is a question. And for that, the best answer is that look at the market trend, right? In x-axis, we have taken the years 2022, 2032. So it's a relevant, time period for people who are you're looking at GenAI now. In y-axis, the revenues made out of GenAI, right? The blue one is representing, the bar chart is representing the revenue made out of GenAI across all the industries in the world over the years. From 2020, it is less. As the years goes by, now we are in 2024, right? We reached a reasonable height, But you see, what we are supposed to reach after, maybe next 10 years is huge, right? And we are only here. You can see in 2032, this much revenue will be generated by GenAI, which means if somebody is taking up GenAI as their career, there's a good possibility that, they will get, a good job and a high paying job and so on, right? The other trend on the expenditure made by the GenAI companies, right? What do you mean by expenditure made by GenAI companies? First, they have to recruit people, one. Second thing, they have to establish computing resources, two. Third one, they have to generate data, gather data, and for all this, they have to spend money, right? And if you see the orange color line, the curve, it goes up, right? Now the spending made by different companies across the world is very less, whereas after some years, you see it is going up, 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 up. So that is a good indication that companies are going to recruit more GenAI engineers. Right? These are the motivations for looking at GenAI. Now let us see how the GenAI is evolved over the years. Right? We are talking about this GenAI last 10 years or 15 years or whatever, after the advent of this, deep learning. But, if you look at the very first contribution to this GenAI, or in particular AI, in general AI, the ELIZA, which is a first chatbot, that is doing the job of the typical GenAI task that we are seeing now. And it was given by an MIT professor. His name is Joseph Weizenbach in the year 1966. And, so how many years back? I don't know whether that professor is still continuing there, maybe retired. And in 1980, after a few years, 1980, autoencoders were introduced by some engineers, and that was introduced for dimensional reduction, right? They didn't have this generation in mind, but they want to reduce the feature vector dimension, right? Those who have studied pattern recognition machine learning may know that, there are many dimensional reduction algorithms like LDA, PCA, ICA, and so on. And this is one of the dimensionality reduction algorithms. So yeah, after some years, in 2011, Siri, which was a powerful, voice assistance, personal voice assistance, it was made by Apple, and it's still in use, and it's a very powerful assistance, personal assistance. Right, in 2011, just before the advent of the deep learning architectures, late 2011 and beginning of 2012, the deep learning architectures started coming. And after a couple of years, the VAE, variation autoencoders, were introduced in 2013. And then GAN was introduced by Goodfellow in the year 2014. And what is GAN? What is GAN? Generative adversarial network. Right? We will see the details of the architectures of that. And Anne Goodfellow has written a nice book on deep learning. Those who want to do research or want to study more on deep learning should necessarily read this book. It's a good book. And then in 2017, CycleGAN was used, but it is introduced. It was slight modification done to GAN. And then 2017, Google researchers developed something known as a transformer. It's also a deep learning architecture, but it is very different from the previous architectures. We'll see the details of it. Then based on the transformer, BERT was also introduced by the same group from Google in the next year. And Robert is also introduced by Google people in the next year, 2019. So on the other side, OpenAI also started looking at the transformer and wanted to bring some models, and they built models like GPT version 1, 2, 3, 3.5, 4, and all that. The version 1 came in 2008 and 2, 19, 3, 20, and 4 in 2013, sorry, 23. Right? And Google also started exploring this transformer concepts for solving various other problems, particularly for text-related problems. And they made T5 and then OpenAI, not just for the image text, they used GPT. They also used GPT for image generation, and it was called as Image GPT, and that they did in the year 2010. And in Image GPT, GPT-2 version was used. GPT-2 was introduced in 2019 for text first, and then it was modified to make it possible to generate images in the year 2020 by the same OpenAI group. Then OpenAI also went on to make another image generation model called DALL-E, and in the year 2021. And this diffusion model was introduced by a company called Runway Research in 2022. And then the OpenAI people integrated this GPT models to make a commercial tool called ChatGPT. Right. So what is the difference between tool and the model? The tool is what's useful to the people, right? And the tool will have the model inside it, right? So it will take the output of the model and it will do something else on top of that, and it will give the answer or solution to the problems given by the users, right? So ChatGPT is not a model, it is a tool, whereas GPT is the model. The recent ChatGPT is involving GPT-4 model. And recently, ChatGPT was integrated into the Bing search by Microsoft, and ChatGPT version 4 was introduced in the year 2023, as I already told. Okay, so let us quickly take an example of generation. What is generation? For example, I am saying I'm giving input image. Input is here. I'm giving input, text input as this: an armchair in the shape of an avocado, an armchair imitating an avocado. And for this statement, the output generated by this DALL-E model is given here. These are all images generated on seeing this text. This text is given by the user, and these images are generated by this DALL-E model. Right? But during the training, the pair of text and images were fed into the model, and the model got trained. Right? When it is deployed, the user is not necessary to give any other thing except this text. This text is called as text prompt, right? The command. The moment the user gives this command, the model will give these kind of images. Is it not interesting, right? Suppose you want to generate a lot of data, image data for training purpose, for any other purpose. You just give the command to the model in terms of text, and the model will give the images that you want. And semantics of these images are matching with the semantics of this text you are given, right? Have you heard? Have you seen the fruit called avocado fruit? And if you open it, you will see two layers. The outer layer is green, the inner layer is brownish, and you will see the same style of color and layers are preserved in the images of the chairs. These are all different designs of chairs, and you see different colors of layers like this. And remember, none of these images may actually be fed into the model during the training. Similar images would have been given, but not exact images that were produced as output by the model. Okay, any query so far? Before getting into specific models, let me take some questions. Any query? Somebody say no query at least. just to check whether you are connected or not.
Okay, sir.
Sir, so far it's clear, sir.
Okay, right. So let us look at the specific models. First model is autoencoder. So for every model, there are two stages, in fact, three stages. What are the three stages? Stage one, training stage or training phase. Second one, testing or validating phase. Third one, deployment phase. Many times we'll give only one diagram and we'll try to explain all three. People may get confused. So if you have any queries related to distinguishing, these three different phases of the SIM model, you may ask query, and to save space and time, normally we'll draw only one diagram. With that diagram, we'll explain all three stages or phases. Right. So let us take this model. During training, what will be done here? During testing or validation, what will be done? During deployment, what will be done? All three we'll discuss. During training, what we give is that we give an input image X, right? The output image X hat will be generated by this model. Initially, this encoder will transform this into some Z, right? That Z will be transformed by this network into Z hat. Z hat is the output of this X. So during training, what we will give in addition to this giving X, right? We will also take X here and take the difference between that X and this X hat. What do you mean difference? You can take now of X minus X hat, or you can take some other distance metric between this X and X hat. In other words, difference between X and X hat, you find the difference, you define the way you want. Okay. If the distance or the loss or the difference is less between what is generated, what is given as an input, then you go and update this theta and phi, meaning you change the parameters of encoder and decoder, the values of the parameters of encoder and decoder, and then again you feed this X into this and see what kind of X hat is generated and see the difference between X hat and that X, right? If it is more, then again you updated it, right? Update this theta and phi and keep doing it. Suppose at some point in time, the X hat comes out to be same as X or very close to X, then you stop. This is what done in training. Any query? What is encoder decoder? Encoder is one deep learning architecture. Decoder is another deep learning architecture. Right? The schematic indication of saying this vertical line is larger, this vertical line is smaller, says that the dimension of the input vector is high, the dimension of the output vector here is less, meaning the dimension of Z is less compared to dimension of Z. Right? We say this Z as the pattern vector or representation vector, which is representing X, or it is called as latent vector. Right? This X hat is considered as the generated image, right? Or predicted image from this Z. So decoder is basically doing the job of generating. Encoder is doing the job of giving the representation of X. The representation of X is Z. Is the training phase clear? Okay, Eileen?
Yes, sir.
Right. So let us come to testing phase. In testing phase, for the X given here, you will get X hat and see for how many images X hats are properly generated, which are similar to X or not, and thereby we will say the accuracy of the model testing. So what is done in deployment? The deployment, we only deploy this decoder, not the encoder, right? And when you deploy decoder, how the user will use it? What is the use case of decoder alone architecture. See, decoder input is some latent vector, right? User may give some vector as input to the decoder. Decoder will generate XFAT, right? The user doesn't need to start with an image and get the Z. It can give any Z. You may be wondering how it is possible for the decoder to convert the Z into X hat, which is similar to some X. That is where the eureka effect of this architecture. What is the eureka effect? Something which is not discovered, right? The way in which we train this architecture is helping us to generate images from random, similar to random vectors Z. Right? If that random vector is close to some actual vector corresponding to X, then that image will be generated. Right? So that is what making this architecture is so wonderful and novel. Let us see what happens here. Assume that this Z vector is of 2 dimension. So x-axis representing 1 dimension and z-axis, y-axis representing the 2nd dimension. Right? So when you take images of all the dogs, for instance, and take corresponding Z vectors, they all are coming here. Let us take all the cat images and take this representation with Zs and plot them. They are all coming here. In general, for a group of objects, you'll get one group of latent vectors here. How do we know this? We experimentally, observe that the grouping is done like that. That is what we say eureka. Some discovery happened. Right? Human mind will suspect that why it happens, but it happens. Why it happens? Because of the learning is done that way. It is capturing the similarity of objects of same type, and therefore the representation of all those similar objects are almost similar. Therefore, in the representation space, they are all coming close to each other. So this is of one category, this is of another category, this is of another category, and so on. Right? And some very different dogs images may come like this. Right? Suppose you take some dogs that are having short legs and so on. They are also, although looking like dogs, but very different from other dogs. So they are forming another small clusters near to the larger cluster. Like that. So this is what the power of the encoding done by the encoder in the autoencoder architecture. So every Z, single Z, is represented a single point here. Okay, but what is this decoder doing? The decoder is taking a single point here, converting back to some dog or cat or whatever. Right. Any query on autoencoder? Autoencoder consists of 2 architectures, right? Deep learning architectures. One is called as encoder, the other one is called as decoder. Just name. Right? Encoder is giving some shorter output vector, and decoder is taking shorter output vector and converting that into something which is same as or similar to the input. So is it supervised? Quick query. Is it supervised? I kept some of my scholars to answer my queries so that I can see whether it is connected or not. Divya, is it supervised? Is the training supervised? Or some other participants also can answer. Unmute yourself and answer. Divya is there?
Yes, sir. She's
Eileen?
connected.
Yeah. Eileen, what is your answer? Is it supervised or unsupervised?
Sir, according to me, it is unsupervised.
Yeah, according to everybody, it is unsupervised. Because we are not saying anywhere whether this X is image of a dog or cat, right? Only X is given. Right? But for finding the loss function value, we need ground truth. right? But here in place of ground truth, we are taking same input x as the ground truth, right? So when you find the loss function value, we find the distance between this x hat, which was generated by this decoder, and the x itself. So x is acting as the ground truth. So you should not say that it is supervised because we are comparing between x and x hat. We are saying it is unsupervised because we are not involving the class label. We don't say whether x is representing dog or cat or whatever. Therefore, it is unsupervised. Agreed? Is there any counterpoint, counter queries? Right, let me move on. Next architecture
Yes,
is,
sir.
yeah. Next architecture is variational autoencoder. Slight modification done to autoencoder. I know there are many researchers available here in this group. Should know what is novelty in a deep learning architectures. Without knowing that, you cannot make one. And if you don't make any novelty in the architecture, your paper may not get accepted in a good journals and conference settings. Let us take that as a case study. See, we already saw autoencoder. The next development is variation autoencoder. How this variation autoencoder is different from autoencoder we need to see, and that difference is what we say novelty. Okay. So in autoencoder also we had this input image x. Here also we have no change. There also we had encoder. Here also we have encoder. Right. X is given as input to encoder. No change. But here the encoder is generating one mean vector and standard deviation sigma. There, what was this encoder generating as output? That is Z, a single vector. But here the encoder is generating two vectors. One is called as mu, the other one is called as sigma. You may be wondering, how do you know that it is a mean and standard deviation? See, we make this architecture to generate two vectors. One we call it as mu, the other one is called as sigma. Then where is the naming convention or the significance of the name, calling it as mean and sigma? That will come later. Now you just assume that this one vector, this is another vector. That's it. From those two vectors, we generate a new vector z by using this formula. So we take mu plus sigma multiplied by the epsilon. The epsilon is basically a number, real number, which is coming from the Gaussian distribution with mean 0 and standard deviation 1. Understood? Right. And this Z is basically a Gaussian distribution because this epsilon is a Gaussian distribution variable. Right? And this Z is given as input to decoder. If you look at the decoder part alone, there also decoder is getting Z as input and generating X hat. Here also decoder is getting Z as input and generating X hat as output. Then where is the difference? Difference comes only here. Right? The Z is not the direct output of encoder, rather Z is indirect output of encoder. What do you mean indirect output of encoder? Encoder is only generating two vectors mu and sigma. With that we are computing Z, right? So Z is computed indirectly as an output of this, right? Okay. Now let us come to the naming convention of calling this vector as mu, calling this vector as sigma. See, when you make this formulation, mu plus sigma times epsilon, mu is a constant because it's already generated. Sigma is a constant generated. Right? When you multiply this random number, which is generated from Gaussian distribution, then this will also be a Gaussian distribution. Z is Gaussian distribution. For this Gaussian distribution, what does the mean? Mean is this. What is the standard deviation? Sigma is the standard deviation. Understood? So we are saying mean and sigma earlier, and we are making sure that those mu and sigma are mean and standard deviation of the random variable z. Make sense? Any queries so far? As I told, during training, we want to make sure that x hat is as close as possible to x. So we find the difference square between this x hat and this x, and the training will go on till this difference is minimum, right? Once it is found to be less than some threshold, we will stop the training and we go on to testing. Further, we'll go on to deploying the model into some web application or desktop application or some other server-based applications, or even mobile applications. Is that clear?
Sir, can you repeat again how Z
Yeah.
is generated?
Sorry?
Sir, can you repeat again how Z is generated?
Yeah. So Z is generated by using this formula, mu plus sigma into epsilon. For a moment, you assume that mu is one dimension, sigma is one dimension, and epsilon is also one dimension, right? And the epsilon is coming from normal distribution or Gaussian distribution with mean 0 and standard deviation 1, right? So if this is Gaussian distribution, then Z is also Gaussian distribution. Mean of the Z will be mu. The standard deviation of the Z will be sigma. How do you know that? That fundamentals you need to look at in probability theory, and straightforward you can prove that. If sigma, I mean, the epsilon is standard Gaussian distribution, and if you take two constants mu and sigma and use this formula, and the random variable Z is made out of this formula, will be again proved to be Gaussian distribution whose mean is mu and standard deviation is sigma. Is that fine?
Yes, sir.
The encoder will throw two vectors as output. One vector is mu, the other vector is sigma, and use them in this formula to get Z. Okay?
Yes, sir.
Fine. Well, how do you say that, this variational autoencoder is better than the autoencoder? If you are a researcher making, let us say, variation autoencoder for the first time, and it is your job to say that this variation autoencoder version is better than the autoencoder version. So the autoencoder will give the latent space like this, representation space like this. Whereas this variation autoencoder will give the representation space like this. What is the difference between this and this? You see, this is kind of continuous. Everywhere data points are there. Here you have a lot of gaps. So when the decoder is picking some data, let's say from here in the autoencoder, its output will be kind of random. That will not be similar to dog or cat, or it will be completely random, right? So therefore, if you deploy the decoder that is coming out of autoencoder, you should be prepared to see some unexpected results. Whereas if you use this variation autoencoder, right, if you see some gap somewhere, small gap may be there. With high probability to hit the points, even if it is not hitting, if you take some point, and corresponding to that, if you get the output of decoder in variation autoencoder model, you'll get a good output because nearby some points are there. The distribution of the data points in the representation space is kind of uniform. Not probability is uniform. What I'm trying to say is spread out. But you can see that, in the middle, the density of the data points is more. As you go away from the middle, you get lesser density. That is what we say as this Z is distributed with Gaussian distribution. Probability density function of Z is Gaussian. You see in the middle, high values, more values are there. As you go away, less. See, Gaussian distribution will have the bell shape, right? If you look at 3D bell shape, if you fit here, right, at the center you'll get a high peak, and as you go away, you'll get height is less. Okay. So this is how you need to justify that the newly created model, the modified model, is better than the previous model with theoretical reasons. Of course, experimentally also you can show that the performance in terms of accuracy, precision, recall of the classification or any other downstream task, you can prove that, justify that. Well, let us try to understand more about this. Let's say the whole space, 2D space, is representing the latent vectors. Let's say here you have the rhombus, here you have rectangle, here you have ellipse, here you have triangle. Suppose you take a point close to this and feed that point Z as input to the decoder in the very hard encoder. That will give something like this. Now, because this point is close to this, so that will also represent this. Suppose you take a point close to this, the yellow color one here, right? And that will, if you take a point here, it will give rectangle. But this point is not close to this, not close to this, in between these two, right? Then property of this and this should come in a blended way, right? In a mixed way. That's what coming here, right? And it is a polygon. It is having some properties of this, some properties of this. Similarly, if you take a point somewhere here, it will become ellipse. And if you take a point here, it will have some properties of this mode and little bit of this and little bit of this. Okay, any queries so far? So what is the time? Time is 11:15. So 45 minutes over. So we'll break for 5 more minutes and then we'll come back, take tea or water, whatever, and then we will start again. Take some water and come. I'll also take water and come. myself, Shahrukh. Yeah, I'm an online talk. Yeah, after that, I got it. Shall we continue?
Yes, sir. We can continue.
Right. Yeah, next we will see one more variant of this autoencoder, variation autoencoder. For that, we need to develop some theory. One theory is visual codebook. To help you understand visual codebook, just think of a dictionary of words, right? Similar to that dictionary of words, you can also make dictionary of image patches, right? And then you can make dictionary of vectors of image patches. That vectors of image patches is called as codebook, visual codebook. The word visual means image. Codebook means dictionary of codes of the visual patches or image patches. That way you can in general define. Let's see how it is done. So as I told, visual code words are base elements to describe an image. Given the whole image like this, to represent this, take the patches. This is one patch, this is another patch, this is another patch, this is another patch, and so on. For every patch, you get a code. Code means representation vector, right? Like that, you take for so many images in the database, right? And some codes will be repeating, some will not be repeating, right? Now you take the union of all the code vectors, and that code vector union is called as codebook, right? The question is that how do you take the patches? For getting the patches, you use some algorithms like SSCET or SURF or Harris corner point detection algorithm. All this will give some corner points, some important points. Around that corner, suppose this is coming as a corner point or important point, then around that you put a window. Take that window patch of image, right? Like that, for every corner point or important point, you get a window around it. that is how patches are taken. And you can find the descriptor using a shift or surf, and that will go as the code word for the particular patch. Code book means set of all code words taken for all patches of all the images in the database. Right? So this is what this schematic diagram represents. So take the patch, get the features using the surf or shift that is represented by this. And this X1, X2, X3, X1 is a representation of patch 1, X2 is a representation of patch 2, and so on. And these are all some d-dimensional vectors. And you see, if X1 is coming again for some other patch from some other image, keep only once X1. Similarly, X2 also only one should be kept. That is what the meaning of union of all the patches, right? So this is the schematic diagram of one example of code book. In this code book, you see each cell is a code. Now what do? Take codes like this and take the clustering of all the codes, right? Like this. And then take the histogram of the code words. For example, a particular code word is coming n number of times. Then for that particular code word 1, the height is representing frequency, and next code word height is represented by the frequency, and so on. So this is called as bag of words. Bag of words is nothing but the frequency of words in the code book. To that. So let us use that for further discussion. And one more concept I want to introduce, something known as vector quantization. Vector quantization is a well-known term in pattern recognition machine learning. What it is doing is that it is transforming n-dimensional data into a k-dimensional discrete data where k is expected to be much less than n. For instance, k is 3, I'm sorry, if n is 3, k is 2. Three-dimensional vector is converted into two-dimensional vector. In a way, this vector quantization is doing dimensionality reduction. Then what do we call this as a dimensionality reduction? Although it is doing dimensionality reduction, it is putting one more constraint. What is that constraint? Discreteness, right? The values of the output vector are all discrete in nature, right? Whereas in dimensionality reduction, the output vectors may be in discrete domain or continuous, and both are there. But here, necessarily, it should be in discrete domain. Any query?
Sir, your camera is closed.
Yeah, I purposely made it to reduce the bandwidth requirement. Do you want it to switch on?
Yes, sir.
Okay, I'll do that after taking my tea. Any other queries related to the concept?
Actually, excuse me, Professor. If you quantize the particular, did you hear me? I'm Satish here. Now, if you quantize the matrix of n dimension, is there any impact over the accuracy of the particular?
Any? Sorry, repeat. Final query?
No, just if you quantize the particular matrix, is that provide any impact over the accuracy?
Impact over accuracy. Accuracy, not necessary. It all depends on
accuracy of the prediction.
Vector quantization. For instance, if you have a feature vector dimension 100, right? If you work with the classifier that takes 100 dimension feature vector, the classifier will take more time to classify, right? Because dimension of the vector is 100. Suppose you want to reduce the time taken by the classifier, you can convert the 100 dimension vector into some 3-dimensional vector, 4-dimensional vector, and train the classifier, right? When you deploy that classifier will work fast because it has to work only with 3-dimensional vector. So in terms of time requirement, this vector quantization will be useful. One. What you're asking
Actually,
in terms
vector
of
quantization
accuracy,
seems to be you are in the context of reducing the shape and size of the vector. No?
correct. Shape I am reducing, meaning the
So
size I am reducing.
I'm talking about the quantization in the aspects in the context of the size reduction.
Yes, size is reduced, right? The input size here is n. The output size is k. K is less than n, right?
Okay, thank you.
Yeah. So, but more important thing is that in terms of accuracy also we can make some contribution if you do vector quantization. Okay? Those who have studied pattern recognition can remember there is a concept called curse of dimensionality, right? The classification can occur better in lower dimension than high dimension. That is called as curse of dimensionality. Just because you have more dimensional vector, it's not that you have more information that will be useful to better classification. No. Right? If you increase the dimensionality, there's a curse, meaning there is a demerit issue in terms of classification. There's a possibility. And what this dimensionality techniques like quantization, vector quantization will do, it will convert the larger dimensional vector into small dimensional vector such a way that when the classifier is using small dimensional vector, it will work well. Right? Just converting larger to smaller is not good enough. You need to convert such a way that you are retaining good information, discriminating information in the smaller dimensional vector. Okay. Does it make sense?
Yeah, fine.
Yeah.
Thank you, Professor.
Right. Let us see how that vector quantization is used in variation autoencoder. Remember, we started with variation autoencoder. Then we modified that to get we started with the autoencoder. We modified that autoencoder to make it variation autoencoder. Now we are changing variation autoencoder to get another version called vector quantization variation autoencoder. This is how the new knowledge is developed. Right? You see here, for a moment you forgot about it. In variation autoencoder, input is converted into some mean and standard deviation. From that, Z was constructed, right? And then from that, decoder is done. So this part is same. Even this part is same. This part is the extra thing, right? What is extra? This is basically encoder. This encoder is transforming this into representation vectors, Z, right? That Z vectors are quantized into this, E1, E2, E3, and so on. E1, E2, E3, and so on. This is the generated vectors. These are all quantized vectors. Remember the quantization technique, right? If it is 4.2, the quantized version of that will be 4, right? So these vectors, ZE1, ZE2, ZE3, and so on. These are all encoded vectors for the given input image, and their corresponding quantized vectors are this ZQ1, ZQ2, and so on. Okay. To get this is the network. For this network, these are all the E1, E2, E3 are all the vectors. Right? It's not theta, it is E1, E2, E3. What is this? This is basically code book. All these are codes, E1, E2, E3, and so on, EK. And these are all standard vectors. And these vectors that are coming out of this encoder may not be matching exactly with any one of this. Then whatever that is closely matching will be the final encoded vectors corresponding to this, right? If this is 4.2, right, 4 is available here, then 4 will come here, right? If it is 3.8, let's say 3 is also there, 4 is also there, then 4 will come here, like that. For one dimension. For multi-dimension, accordingly, quantization is done, right? So the output vector is quantized and then fed into the decoder. Therefore, it is called as vector quantization. The quantization is done for the vectors, not for one single number. Let us see the loss function. For any architecture, loss function is a vital one. That will be, defined properly to get the desired result. In this case, there are three components. What is the first one? Given ZQX, you need to generate the output which is similar to input. Input is X, right? So output is expected to be X. So X should be generated from this with very high probability. So probability of generating this X from this ZQ should be one parameter. Why we want to take logarithm? Logarithm is basically changing the scale, dynamic scale of the number. Then what is the second term? Second term is telling the difference between the ground truth E and the output of the encoder ZE of X, right? So whatever that comes out of this, right, should match with any one of the predefined codes, right? And it should be as close as possible to that. So the quantization is done based on this, right? And this also is talking about quantization, but that SG function is applied for this here, and here SG is applied for E, right? So if you take this term, ZE of X and E, in both cases, you have the same. Only thing is that you apply SG for this, whereas SG for E here. So all these three terms are to be, looked at, all are contributing to the optimization function, the loss function. You need to minimize the loss. Maybe wondering, say I need to maximize the probability, then why you want to minimize this? See, the probability is negative. So I'm sorry, probability is from 0 to 1. Therefore, when you take logarithm of the fraction from 0 to 1, it becomes negative. So therefore, you need to minimize the negative values, right? Well, let us look at this. This is another version. Earlier we looked at vector quantized variation autoencoder. Another variation to VAE is discrete version of VAE. So here what we do, as we did earlier, this encoder part is same, and it is giving some output, and there the output was quantized by the codebook. But here, instead of quantizing it, we are learning the probability distribution of all the codes corresponding to every vector here. This is the encoded vector. Corresponding to encoded vector, we see which one of the code in the codebook is giving good probability, high probability, low probability. That complete probability distribution we use. And that is combined with this output of this one. Softmax is applied onto this vector, and though both are combined together, meaning they are multiplied. We'll see how they are multiplied, and the output comes. That output is given as an input to CNN, and this CNN is giving this images output. This CNN is called as decoder. This is called as encoder. In between, we do a lot of changes compared to what we have in the previous version. Any query? Only thing that we need to look at is how this operation is made. So what is the difference between discrete VAE and quantized, vector quantized VAE? Is there any probability distribution for codes in the codebook here? But here we have probability distribution for codes in the codebook. That's the vital difference. Okay, right. I told how to multiply this, right? So image is given as an input to the encoder, and that is giving probability distribution of latent vectors here, and that will be multiplied with code book vectors. We will see how it is done in the next slide. You see here. So this is the probability distribution of the latent vectors, and that probability distribution is converted into another probability distribution by using a function called Gumbel softmax distribution. That Gumbel function is transforming a discrete probability density function to continuous probability density function such a way that the difference between continuous probability density function and discrete probability density function is the least. So this discrete version is converted into the continuous version. Then such continuous probability densities were multiplied with the corresponding code vectors, and they are all added together. Right? This is what represented by this symbol. Okay. Okay. So the Gumbel PDF is defined as this. This is basically converting the discrete function to the continuous one. That continuous function will mimic, right-tailed Gaussian distribution like this. If you change the parameters of the distribution mu and beta, accordingly, this shape will change slightly. And the formula for Gumbel-Sopwith function is written here. So let us go on to the next model. Before going next model, if there is any query, please get it clarified. Remember, in all the previous models that we looked at, there are two components, encoder and decoder. But we use the word encoder only in the title of the model, auto encoder. We are forgetting about the decoder part in the title. Therefore, if we try to get the meaning out of the title itself or name itself, sometimes go wrong. This is an example. Although decoder is also there in the architecture, in the name decoder is not mentioned. Okay, I switch on my camera. Shall we go on to the next model? Some of you please say yes. I want to check my connectivity.
Yes, sir.
Yes, sir.
Right. So next model is GAN, stands for Generative Adversarial Network. This also has got two architectures, meaning two deep learning models inside it. One is called as Generative G, the other one is called as Discriminator D. What is the role that needs to be played by generator? Generator will take some input, some random input, and will generate some image, maybe random initially, right? And the discriminator will take the output of generator and one target real image. If the generated image is different from target image with respect to the discriminator's point of view, it will say, no, they are not same, it will say. When say, yes, they are same, it means they are same, right? So it will find out whether they are same or different. Right? If they are same, we can say it is real or it is called as fake. Different jargons are used. Let us not use the word real and fake. Let us use that whether generated image is same as the target image with respect to discriminator or not is a question. If it says yes, same. If it says no, not same. Suppose it says no, which means the target image and generated image are not the same. In that case, we'll update the weights of generator and discriminator again. So we keep send the input to the generator, same input to the generator. generated, and now it will generate different images because weights are updated. So now it will check, the discriminant will check whether generated output and the target image or data are same or not. Suppose again it says no, then again generative will be updated, discriminator will be updated. It will keep on going. At some point in time, discriminator says no, the generated output and the target output, right, are the same. Suppose it says, then it will stop. As long as it says they are different, then the change in weights of generator and discriminator will go on. Once discriminator says no, they are not different, yes, they are same, if it says like that, then it will stop. Make sense? So then how do you build this generator? How do you be discriminator? You make some CNN architecture or DNN architecture here and here, right? With some intuition, or even without intuition also some people are doing it and getting the task, performing the task. So where's the novelty brought in when you want to make your own GAN? So the overall architecture is known to everybody, but you can bring novelty in making generator and making discriminator for the problem that you want to solve. Is that right? So next model is transformer. Let us see, what is the impact of transformer first, then we will see what is transformer. Of course, you can learn things in a bottom-up way or top-down way, right? Both are fine. One way is that you can study what is transformer and then you can find out, where are it is used and so on. First, you can, look at, what is the benefit of studying transformer in terms of the applications, and then we can study the transformer. Both are fine. So we are choosing the second way here. So transformer was used to build some very successful models like BERT, GPT, and so on. BERT was built by Google team. And from BERT, Roberta was also built by Google team. Transformers were used by OpenAI, and they built GPTs, different versions of GPTs. One interesting thing is image GPT, that is also coming out of transformers only. The transformers came with the idea of self-attention. This is a watchword. Self-attention. We'll see what is it. It extracts the information from whole sequence. The information is nothing but weighted sum of all the past encoder outputs. States are meaning here outputs. The transformers completely removed. The transformers have completely removed the idea of recurrence that is there in the recurrent neural network, and it is also not involving convolution. If you look at the previous models that we looked at, like autoencoder, variation autoencoder, and vector quantized variation autoencoder, they're all now we have two networks called encoder decoder, right? They can be built using CNN, but these transformers have not brought anything like recurrent network or CNN, right? It is free from those two. One applications of not involving these two things is that you don't have to build a heavy model for making good representation learning. The transformers models were tested successfully on English to French and English to German initially. Now it is being used left and right. From any source language to any destination language, you can use this transformers. Let us see the architectures of transformers. Let me zoom it. I don't know whether it is readable. Is it readable? The texts are readable?
So a little bit it can be increased.
Right. Is it okay now?
Yes, sir.
Right. So forget out this NX. You just look at this portion and this portion. The input is coming here. What is the typical input? Maybe a text prompt statement. Hi, how are you? Maybe like that. And that sequence of words will be converted into sequence of vectors. Every word will be converted into some vector, and sequence of vectors will be converted into concatenated version of sequence of vectors. And every word will also get its position encoding. First word encoding followed by its location encoding. Second word encoding followed by second word position information. All that will be sit together to get a large vector, pattern vector. That will be fed into this big box. Big box, right? One input is what? The text statement that you gave us input, right? That is converted into some vectors with numerical values, right? That contains information about the words themselves and also the respective position of each word in the statement. Fine. That goes as the one dominant input to this block called multi-head attention block. This is a function, a functionality. That functional unit takes three inputs. One is this, right? And then the same thing is again, duplicated. So the embedded vector that goes as are considered three times, replica of that is considered, and three inputs are fed into multi-head attention. In fact, only one unique input that is replicated two more times, and three replicated vectors are going to the multi-head attention. We'll see what is multi-head attention later. Just take that as a block box. Second. And then the output of that is added with the embedding of this sentence, right? Both are numerical vectors, therefore you can add, and the dimension also kept same, therefore addition is well defined. And after adding, you apply the normalization, min-max normalization or batch normalization or whatever normalization you want, right? You do some normalization. Then that goes as input to the next layer called feed forward fully connected layer. And that is going as an, that feed forward network will give some output, that output is added with the input of the feed forward layer, right? That sum of those vectors is again normalized. And the normalized vector will go as an output that will be given as an input to this module. Again, there is another multi-head attention in this block. See, this portion is called as decoder. This is called as encoder. Understood? Any doubt in the encoder part? So the decoder is getting some information from the encoder. Okay. Now let us look at the decoder part. So decoder is also getting some specific input. So let me fix the context for better understanding. Let's say input is நீங்கள் நலமாய் இருக்கிறீர்களா in Tamil. நீங்கள் நலமாய் இருக்கிறீர்களா. Right? During training, I'll give one input, right? I'm saying it is an output. During testing, this will become output, right? But during training, I'll give input to this, but that input is expected to be an output of the trained model, right? Just consider that, I'm giving one input here, another input here. Forget about the word output for a moment. Now it is a little bit confusing. Later it will be clear. The input, for instance, நீங்கள் நலமாய் இருக்கிறீர்களா. The output is how are you, right? So initially for training, the input நீங்கள் நலமாய் இருக்கிறீர்களா I'll give to this network. How are you I'll give as input to this network. Okay. So what is this network doing? How are you will be fed here. This block will convert into some feature vector, and then the position embedding will be done with that feature vector, and that will go here, and that will be replicated 3 times, and all 3 will go here. This masked multi-head attention, we'll see what is masked multi-head attention a little later. It considers a block box, and so this is giving output. That output is added with the input of this, right? The input is coming here, right? And then normalization is done. That is going as one output here, Remember, another output is coming here. That is replicated once more. So two inputs are coming from here to this. One is coming from the output of this. So these three things are fed as input to this. And it is giving some output that is added with the input of this and normalized, and it is given to this layer as input, and is giving output that is added with the previous layer, output, and then again it is going through some linear layer, and then it is going to softmax function, and it is giving the probability distribution of the next word. For example, when I give hi, how are you, the next word will be predicted by this model, say encoder, and there will be several candidate next words, right? For each candidate next word, the corresponding probability will be given as an output by this model. So what is the overall input output of this transformer? The input will be here, let us say sequence of n words. Output will be the n plus 1th word that is predicted by this. To predict the n plus 1th word, the transformer will take first n words in the target language, and also it will take their corresponding source language information, and it will predict the next word. For instance, I make this example. Hi, how are? That is what I gave as input here. Hi, how are? Suppose here I write Nalama irukkrீர்களா here. Right? This part of the transformer will output U. However, was input, the next word that is to be predicted is U. That will be predicted by this portion. To predict that U word, it is taking however and also some information, representation information of the corresponding source language text. Got it? Here we made some assumption, block box assumption, particularly this multi-head attention and masked multi-head attention. We will see that in the subsequent slides. Any doubt? Well, okay. So I go back to So as we have seen, there are three parts here, basically two parts. In that, each of the two parts, one more part is there. This is encoder, this is decoder. Inside the encoder, multi-head attention is there, masked multi-head attention is there. They are basically attention module. So that attention module is written here. So encoder, decoder, attention module, right? The encoder is basically transforming the input sequence to the corresponding representation vector. The decoder is transforming here input sequence of words to the next word in the sequence, right? And the attention is basically executing this function, Q transpose KV, right? V is transformed into the scaled version of P. That scale is defined by Q transpose K. Q is one vector, K is another vector. And Q transpose K will be a scalar, which is acting as a weighter for the vector V. Well, so now let us look at what is this multi-head attention. Multi-head attention is here. First, we'll see the attention layer, then we'll see multi-head. The scale dot product attention, in short, it is called as attention. The architecture of attention module is this. What is it? Mathematically, we define attention as function of three variables, and the function value is this, right? So it requires three inputs, Q, K, V. Q, K, V, all three are given as input to this module, and this K and Q are multiplied using dot product. That is called as mat multiplication. Corresponding multiplication is done, and matrix multiplication, I mean Q transpose K. Computing Q transpose K is called as matrix multiplication, and then that is multiplied by some constant scaled up or scaled down. Then if you want, you can mask some of the components of the vector. Masking means making it 0. Otherwise, you can remove this component. This is only optional one. Then you apply Sartman's function on this. Then you get probability of every component in the scaled version of the Q transpose K into B. And that you give us input to this, V as input to this. Now you do the matrix multiplication. What is matrix multiplication? What you get is a scalar, and when that is multiplied with V, then it's scaled version of V you will get. Right? So this is what attention module is. Right? In detail, the name of the attention module is also called as scaled dot product attention. What is this multi-head attention? You replicate this many times. Right? Replicate this many times. Over every layer is called as one scale dot product attention. So let us keep some 3, in this case, H number of scale dot product attention are kept like this. And each scale dot product attention will give one output, right? One vector, right? You concatenate such outputs of all the vectors together. You feed that as an input to another module called linear layer, neural network layer, linear layer. And that will give some output. That is a final output of multi-head attention model. The whole thing is called as multi-head attention model. You see here we have multi-head attention model here multi-head attention, but here masked multi-head attention. What does it mean? If this block is present in any one of these layers, then the whole thing is called as masked multi-head attention. Otherwise, it's only called as multi-head attention. Understood? Any queries so far? And another important fact is that this block can be replicated any number of times, n times. This block can be replicated any number of times. So what is the impact of replicating the blocks? If we replicate many times, copy many times, then the accuracy may improve, but training time and testing time will be huge, and even the execution time after you deploy the model, it will take more time because it has to do more number of operations. So there's a trade-off between efficacy and efficiency. When I say efficiency, I mean the time complexity. Efficacy means the precision, accuracy, recall, F1 score, all those things, performance metrics. Right. And with this GPT, let me stop. How much more time left? Maybe with this last slide, I'll stop. Sir, how much more time left? Organizer? Can I take 5 more minutes?
Yeah, sir. You can take 2 more minutes.
Right. And then I'll now answer your queries. See, this transformer is used in all the GPT versions 1, 2, 3, 4, and so on. Right? How it is used, let us quickly see and wind up. See, prior to this GPT model, all the natural language processing models were trained on a particular task using supervised learning. What does it mean? Suppose you want to do text summarization, then you need to build a model. Suppose you want to find sentiment of the author of the text, then you need to build another model. For every single task, you need to build a single model. If there are 100 tasks to be performed, then you need 100 separate models, right? But GPT is trying to make a single model and performing all the 100 tasks. That is the main difference, right? The as I told, the main drawback of supervised learning is to make a separate model for executing separate tasks. Whereas the GPT, which is using the transformer, which is basically unsupervised model, right? What is unsupervised? Not GPT itself. The transformer is unsupervised because, as you know, we are not giving the labels for the input. But we also do some part of supervised learning in GPT that is called as fine-tuning of downstream tasks. For example, if you want to do the classification or doing sentiment analysis or language translation, for the fine-tuning operations, you need to do supervised learning. So unsupervised learning, supervised learning, both are mixed together in GPT. The predominant portion of this GPT is unsupervised model, right? That is called as unsupervised pre-trained transformer. The name of GPT, the expansion of GPT is generative pre-trained transformer. The transformer is pre-trained, that is capable of generating next word. But on top of that, we build some supervised learning models for downstream operations like classification or sentiment analysis and so on, right? And we have GPT-1, GPT-2, GPT-3, and so on. And the difference between 1, 2 is that in 2 you have a little bit more number of parameters. Therefore, it is able to handle more tasks in a better way. GPT-3, even more tasks, more parameters. GPT-4, even more tasks, more parameters. And there is another one called, Image GPT, which is basically using GPT-2 version and making some changes, and it is generating images, right? There is a huge number of, spectrum of image translators like, the diffusion model, that is something known as, DALI 1, DALI 2, and Glide model. All these models are generating images. They are all, making use of the transformers, right? And also it is making use of something else also. There is something known as clip, that is also used in Glide. But the point is that, the transformer is the, the nucleus of all these models. Along with this, there are other portions also in the subsequent models. So if somebody wants to, make a novelty in making, new deep learning models, they can use transformer, they can use existing things, but not just that. Along with that, they should bring something else also, right? That something else that you want to bring is going to differentiate your work from the rest of your works, right? So with this, let me stop. And I have so many other slides. You can go through them later when you're free. And if you have any doubts, you can, mail me and I'll clarify that to you. Okay, with this, let me stop. If there is any query, you can call.
Participants, if you have any queries, you can raise now.
Hope this is slightly different from what you learned earlier. Some participants can answer how much of the overlapping you find between this and the earlier content. 10%, 20%. What is the percentage? Satish, what is the percentage you found?
Sir?
So what is the percentage of overlapping?
Actually, I'm a presenter. Just I want to hear some content. How the program is going on.
Right. Okay. Amjad, yeah. Naveen Kumar, we hope you attended both sessions.
Sir, yesterday we have introduction about GenAI, sir, and afternoon we have session about GenAI in art, music, and literature, sir. So today only we focused on that.
Did you find any overlapping?
Lecture,
how much of overlapping you found between today's lecture and the previous lecture?
No overlapping, sir. So participants, do you have any queries?
So there is one question in a chat box from Dr. Brahampal Singh. How can we relate Gen AI and machine learning?
So how can we repeat?
How can we relate Gen AI and machine learning?
Great. Yeah. For that, we need to know the definition of each of the terms. Right. So what is machine learning? Machine learning definition goes like this. If you mimic the human intelligence in problem solving, then that mimicking is called as machine learning. When I say mimicking, writing program or algorithm that is doing the same thing that is done by the human brain. Right? Understood? That is the definition of machine learning. What is the definition of artificial intelligence? If you write an algorithm, if that algorithm is mimicking the intelligence of any nature, for instance, mimicking the intelligence of cat or honeybee, right, or ant, or human being, or fog, whatever, any natural intelligence we mimic, that is called as artificial intelligence. Okay, so therefore machine learning is subset of artificial intelligence because human being is a natural. Now the question is that how GenAI is related to machine learning. Of course, we can relate AI with machine learning, that is done. GenAI is part of AI, right? But is it part of machine learning also? Right. Make GenAI, if you relate or if you mimic the human way of solving problem, then that GenAI would be called as machine learning, otherwise it is not. Right. But is this GenAI concept that we studied mimicking the human brain? Yes, because they all use ANN. Agreed or not? Artificial neural network. Every block, whether it's encoder or decoder, right? That is found in GAN or autoencoder, variation autoencoder. Everywhere we have this blocks, right? They are all neural networks. How do you relate neural networks with our human brain? Is it not ANN mathematical model of human brain? Is it not that ANN is trying to mimic how the human brain is solving problem? Therefore, GenAI is a subset of machine learning. Make sense? Yeah, the one who asks questions say yes or no. We can make counter questions if you don't get it. You try to compare two different things. Yes, you need to know the definitions of those so that you can compare with respect to definition or with respect to properties.
Okay, thank you, sir.
Okay.
So shall we conclude, sir?
Yeah, please.
So I request Ms. Asha ma'am to conclude the event.
So one more question in the chat, sir. How to address the bias issues of GenAI?
Okay, so when we say bias, there are different types of bias. Let us consider a bias to the data. Okay? In the training, if you have trained the model with examples of a particular category more, then you increase the number of samples in other categories also. That will reduce the bias towards the data. For instance, if your model is trained to learn the feature vectors of the Black American people, then you should give more examples of white Americans to the model to learn features about the white people also. That is how we can reduce the bias to the data. Yeah. Any other queries? Okay, I think it's done. We are running out of time. Close to.
No queries, sir. We will conclude, sir.
Okay, on behalf of the organizing committee and all the participants, I extend our heartfelt gratitude to Dr. B. Masilamani for delivering such an enlightening session on architecture in GenAI, GAN, VAE, and transformers. Your ability to explain complex concepts with clarity, the practical insights and real-world applications you shared along with your engaging presentation had undoubtedly inspired us to explore these cutting-edge topics further in our academic and research endeavors. It was a privilege to learn from you and we look forward to having the opportunity to interact with you again in the future. Thank you once again, sir, and we wish you continued success in all your professional and research pursuits. Thank you, sir.
Thank you. Thank you all. Thank you, ma'am. Thank you all for listening to me patiently. All the very best for your future research or for the rest of the talks in the workshop. Thank you.
I request all the participants to turn on the camera for a photo session.
So, do you want me to stay, ma'am?
Sir, everyone will be.
Do you want me to
turning on the
stay?
camera. Yes, sir. Yes, sir. Just for a few minutes for a photo session. Okay, thank you, participants.